So we are now doing a topographic survey. So we will be putting total station, and the mapping which we will be doing will get the accuracy in millimeter. And this is important because we need to have the accuracy, like was what I told, it's minimal millimeter, but we need this profile to understand that the amount of vertical displacement during different earthquakes. So after the total station profile or topographic profile, we'll be doing GPR, ground penetrating radar, and that will help us in identifying the displacement of the young deposits or the young sediment layers in subsurface. And then after, we will be digging a trench where we will actually see the sediments layer displaced or deformed. So that's what we are going to do now. So slowly we'll set up the total station here. So you see the two red boxes. We have the instruments in that. That is all differential GPS antennas, and then the bigger one box which is coming right now, carried by the team members. We'll set up that. And the unit which they are bringing right now is ground penetrating radar. So this is the ground penetrating radar unit with 350 megahertz antenna. So basically this works on the transmission of the electromagnetic wave, and this helps us in identifying the different layers, and if those layers are displaced, then that structure also we will be able to see in the profile. So this is what I was telling about the GPR. This is 350 megahertz antenna, and right now we are doing the setup. So this is a very compact unit which we have in our lab. And this antenna is hyper stacking, so we get less noise while taking the profile. So right now what you see, we are just connecting the batteries to the antenna, and the wires are already connected to the receiver. The receiver is a tough book which will keep showing us the data in real time. So as we move the GPR mounted on this card, it will keep giving us the subsurface profile. And as I told that this will help us in identifying the different layers, that is the subsurface layers, and the deformation if it was present. But since with the experience we know that this isn't the feature on the surface, what we see is related to the past earthquakes. So definitely we'll be able to see some beautiful deformation features in GPR profile. So basically this works on the principle of, as I told, that transmit the electromagnetic wave, and since the material, that is earth material, and on the surface as well as within the the surface will have different dielectric constant. Hence we will be seeing the profile with what we call line scan. So the transmission of the electromagnetic waves will be measured in two-way travel time, once it goes and then reflected. The beauty of this instrument is that we'll having the data in real time, so we of course we need to process it, but the processing time is reduced because we'll setting up some of the parameters right in the beginning, like what the appropriate dielectric constant will give at what rate the transmission should be, and if the data we want to have or the penetration if we want to increase, then we can increase the gain also. And with this instrument maximum we can go up to 10 meters, but we will be fine if we are having the data up to 5 to 6 meters, because we won't be going very deep in terms of digging the trench, so that will help us. And mostly as we know that this deposits or the material which we see here is brought by the river, deposited by river fluvial deposits. So mostly what we will be expecting is the fine deposits comprising of sand, silt, and then we will have gravel. So we'll have different very good contrast between the sediment succession, and that will be easily the GPR will be able to pick up that part. So what we will be doing, that we'll be taking the profile across this, and so we'll be able to see the subsurface, what type of different deformation or the deformed layers are. So we'll be moving the GPR across this, and then we'll also bring down, we'll take multiple profile, and whichever is the best in terms of the expectation of our the type of the quality of data, mainly what we will get, we'll try to use that one. Okay, so we'll keep, as I told, that we'll keep changing the parameters like dielectric constant will do, and transmission rate and all that, and that will help us in getting better high resolution profile. So now we are taking the GPR profile with 350 megahertz hyper stacking antenna, and what we have, this one is the tough pad in which we will be getting the profile and real-time profile of the subsurface. We have set this unit to take the profile up to 8 meters, and let's see how it goes. So we'll start now. So now we are just pushing the machine. It's a bit hard here because of the roots on the surface and some gravels. So now we are moving on the second scarp. Hopefully, if the smaller one is the youngest, then we are on the third one. It's getting a bit difficult pushing up because on the slope it is not moving. We are trying hard. 3 of us are moving with the GPR. Okay. So now this is the end point, because we won't be able to move further ahead, and this is the point where we have marked, and that will be the line end point, and we'll measure the whole strip, how much meters we have done from the base of the scarp right up to this. So it's getting hard, difficult, but yes, of course we'll have to do the job. Okay. So now we'll be moving down from the top of the scarp, and we'll go to the toe of the scarp. So again, it's a bit dangerous because we have the wheels on the GPR, and this cart can roll down, and so we'll be a bit careful. So we'll see how we can manage to move down on a steeper scarp here. The lower one is fine, but this is quite steep, so we'll have to move a bit slowly, and we'll see, and in between if we get some good structure then we'll show you. Of course, the profile which we took from the base to the top, we got good indications or the signatures of the deformation. It will show when we are moving down. Okay. So let's get started. Okay, so this we started from 0 here, and then we are moving towards down. So what we see here is there is some deformation at this location. Now probably we'll get down here after we cross the second scarp here. So we'll see what best we see in multiple profiles, and one of the best profile will pick up for our final interpretations. So this is how the GPR profile is seen, and this is typically of what we have is the line scan which you saw. So it's in the positive negative pulses we are recording here. Measuring, so we are right now at 10 meters, exactly almost what we see here in the. So we have moved down 10 meters from the upper scarp, and the same you can see on the screen here. So we are up to 10 meters here. So now we are moving down the other scarp, which is smaller one. It's going to be difficult because it is comparatively less slope than the first one, but yes, of course it is moving very fast here. Hold it. Chalo, go, chalo, start. Hold. Okay. Hold. Okay, go. Go. छोड़ दो. So now we are almost on the flat area, but I suspect that there is one more scarp, smaller one. Now we are climbing down of the smaller one. If we see some deformation here, then this will be the most youngest scarp. So this way we are going to take multiple profiles and then see what best we are able to look at the signatures of. Okay, stopping here now, and we'll take another profile, again moving from the base to the top. Okay. So now in this we can also go into the playback mode, and the profiles which we have collected, this was the last profile we collected, and that can be seen here. So this is what we have in the last profile. So if you इसको नैन इधर कैसे मूव करते हो तुम लोग? नहीं आता ऐसे ना? ऐसे नहीं इस तरफ जाना है हमको।
आप वापस से प्लेबैक करिए, जहाँ पर आपको रोकना है वहाँ पर स्टॉप करके एक आएगा। जहाँ पर भी आपको रोकना है वहाँ पर आप रोक सकते हैं।
So this is the deformation what we see here. You cannot go back here. ऐसा तो होना नहीं चाहिए था, होना नहीं चाहिए था ऐसा तो।
इसको खड़े कीजिए। आ रहा है ना?
लेकिन इधर नहीं है। नहीं सर, ऐसे नहीं है।
क्या आ रहा है ना?
हाँ तो वो इधर जाना चाह रहा है सर।
Anyway, चलो इसको बंद कर दो, कोई नहीं। So this probably what we see is the deformed layers and getting displaced along the very shallow thrust fault. So hopefully we'll be getting this structure below, and this goes up to 4 meters here. So we'll be going up to 4 meters at least in the upper scarp, and then further if we move here, then what we see, okay. So this I'll play it again. And then another somewhere comes over here. We'll take another profile and try to see what are the signatures. Thank you. So now we are again taking another profile, and as I told that this is a very young scarp. So most likely we'll be getting something over here at 3 meters. So somewhere around here probably we'll get some deformation, and that's what we have seen in the previous profile. So now we are going up to like 8 meter of depth, but in next coming profiles what we will do, will reduce the depth so that we can get very high resolution data. Chalo. So we are moving up now, the second scarp. So we have already crossed almost like 13 meters now from the base, and we are moving on the other scarp, and yes, we see something here, some offset of the radar reflections on the screen, and that is what we are looking for. So we can see this one, this is in the very prominent feature here, which goes up to the depth of at least 6 meters down.
तो वहाँ बैठ जाओ खाली।
Now we are almost like 22 meters. We have climbed the scarp. Another one. So this is our end point. Again we are ending our profile here. Total we have moved to 27 meters. So now we are going back again from the top of the scarp, moving down to the Indo-Gangetic plain. We are on the youngest mountain chain in the Himalayas, and this is what we told earlier also that this marks the plate boundary. So let's move, keep rolling. So now from here what you can view is right down the Indo-Gangetic plain and the two scarps, or probably the three scarps, which we have been talking about, that there is one youngest scarp there, but that we will come to know maybe tomorrow when we are digging the trench. So we are doing GPR, and then we are on the second, probably second or third scarp, and then we have the total station here, which has also been mounted. And this is important because we, as I told, that we need to do a very precise topographic mapping. So we'll be taking multiple points to have the complete topography of, even if you have like the elevated land surface by half a meter or less than that also we'll map. Okay, that is very important for us. Probably it is, if it is not disturbed. If it is disturbed, then it is not the actual feature which was produced by the earthquake. But otherwise it is important for us because the deformation can result into the development of the smaller scarp also of less height. So this is we have already discussed about this GPR, and then what we are doing here is the total station which has been set up, and then this will be having the capability of laser. So the pole which you see there, the person Ishan standing with the pole, it has a prism there, so this will be focused with the prism there, and then we'll keep taking the points. Now this total station is so advanced that it can automatically take the readings if the person who is moving, that what we call rover, with the prism, and that can be we can. Okay, so this total station what we have is it's quite advanced and very high-end one, which we call the robotic total station, and it can be handled by a single person. And if you see there that what person is handling, Ishan, with the prism, he can collect the readings if the total station is able to see the prism. Okay, and that will be through the laser pointer, and it will connect through laser, and that will keep taking the readings there. So we will be taking, each point will give us XYZ, that is your latitude, longitude and height, and that is going to help us in putting the profile and very perfectly in terms of the elevation and also in terms of the coordinates. Thank you. So we are on the Indo-Gangetic plain, okay, and this is the basin, four-lane basin in the frontal part of the Himalaya. And what we see is, now if you turn around, then we will look at the plate boundary between the Indian plate and the Eurasian plate, where you see the hills starting here, and this is what we have, the uplifted terrace, and this what we call is the fault scarp. Okay. And the portion we have cleaned up, which you can see through the station which has been kept here. This is our RTK station. We are doing the mapping here, and on the top where we have cleaned, if you see that part, that is your fault scarp. And we are trying to look at the signature of the ancient earthquakes in this cliff, or the elevated portion, which we call scarp. It's a fault scarp, and the fault which we have named this as an Kaladungi fault. So right now we have put this GPS station, which is our base station, and we are doing with the help of rover. With the help of rover, we are taking the points. Again, this will give us the XYZ wherever we go and stand, and it will take the points in continuous mode. So we'll get very precise location, we'll get very precise elevation in millimeter accuracy, and that's what we need for the precise topographic topography of this area. That's what we are doing. Along with that, we are also flying UAV to cover the larger area, because it is difficult for us to do mapping manually using the rover. That is, again, on the rover we have another GPS antenna. Because of the dense cover of the trees and all that, we won't be able to get the signals. So it will sometimes it is difficult for us to collect the GPS points. So for that, what we are going to do is we are going to use UAV, and UAV will give us very good at least the elevation model and the terrain around in this area, because it is difficult to enter into the dense forest. So the best way of the mapping techniques which we are using, as we are using all, like the total station, and we are using even the post processing kinematic survey we are doing RTK, real-time kinematic, and along with that we'll be doing UAV. So this what we are showing you is the base station here in the front of the camera. And if you see the long shot, then we have the person who is handling the rover and moving ahead, taking the points with respect to this base actually. So this will give us the precise locations of each and every point. And as I told, that this will, as we walk, it will keep collecting the points, and it will give us the coordinates, that is your x, y, and the elevation also. So now we will be doing GPR, ground penetrating radar, using another model, and with 200 megahertz antenna, and this will give us depth up to 10 meters we can go with this, but we will restrict ourselves going up to maximum 6 to 8 meters. And the previous one which we used before was 350 megahertz antenna. So this is a very simple thumb rule, that if you have the higher frequency, then you will be able to penetrate up to shallow depth, and if you have less frequency antenna, then you will be able to penetrate to greater depth. So with 200, because this solves our problem, and in terms of getting the subsurface profile up to 6 to 8 meters, which is much more enough for putting the trench. And this will also tell us the precise locations of the displaced layers, so that we can go deeper in terms when we are doing trenching. So that is one of the important point here, to use the 200 megahertz antenna and 350 megahertz antenna. The previous one which we used was hyperstacking, and with our experience, this 200 megahertz antenna, we have like good results we got in the past also, doing similar type of survey, GPR survey, for trenching, for paleoseismic investigations in Himalayas as well as in Kutch. So this is going to help us in knowing the subsurface profile. So this is our main unit, which we call the transmitting unit. And as I told, the previous unit also had a tough book, where we used to transmit the electromagnetic wave, and as well as we were collecting the data. And this antenna is also going to transmit and receive the signals, and that will be displayed on this unit. Okay. So we'll have, I'll show you the screen. So this is your screen here. So on the screen you will see all the data coming in. So when we start, we will show you the data, how it is coming. And so we are connecting the cable from the antenna, and now this will go to the new the main unit. GPR profile, and we have named as NP and the date, that is Nandpur, and the date is 9 220, and then we'll say apply. So now we are moving with the 200 megahertz antenna, and the system which we have is SIR 4000. So now the information, subsurface information, is getting displayed here in a form of a line scan.
वाला पैर उठाइए।
बात ही कुछ और है दूसरी टेस्टिंग। तो कितना मीटर आ गया कुछ?
हम लोग we have moved almost 8 meters now. We are moving to 9 meters.
नहीं जा रहा ना?
हाँ वही है।
चलो
पहले यहाँ से नदी बहती है।
So now we have entered into the uplifted riverbed, just few kilometers east of Dapka, and the blue spot shows our location on Google Earth. And what you see here, this is basically the paleo wind gap of Dapka river. Earlier Dapka river used to flow through this one, and now it flows through this point here. So this is the edge of the previous ancient Dapka river, which used to flow through this gap. And the deposits, if you want to see, you can look at over there up. These are all fluvial deposits of Dapka river, and at present what we see is the incised valley by the small channel, but this whole area is the deposits of, you see what we see, the flat surface of the terrace, and the downstream will show another terrace, which is the younger terrace. This is the older one, which clearly indicates that Dapka flowed at that level one point of time. So if we have the age of this, then we'll be able to tell you that when exactly Dapka river flowed at that level. So these are all very important spots to understand that how the landscape got changed because of the tectonic activity in the past. So now today we are finally going to start trenching, and we have this machine here. You can see this we will be using for digging the trench, and as I told, that will be going maximum up to 2 to 3 meters. And this we have done the marking because we need to open the trench exactly perpendicular to the scarp. So if this is the scarp, the trench should be like that. So exactly perpendicular to the scarp, we will be opening the trench, and that will give us the section subsurface. the deformed units, and that is important for identifying the displacements as well as identifying the value earthquakes in this area. So this marking which we have done, so the digging will be done along with this within this portion. So now we have finished the marking, and we will start digging. So what we will do is we will have slightly deeper at the upper part, and then slowly we'll make a ramp so that our machine can come out from the ramp, and we will reduce the height here. So this will be the end point where we will start our trenching. बनाएंगे और सरफेस बिल्कुल क्लीन होनी चाहिए, और जो भी ट्रेंच साफ करेगा ऊपर से, वो ऊपर से शुरू करेगा नीचे तक आएगा, ठीक है। तो ये नहीं होना चाहिए कि आपने क्लीनिंग करना शुरू किया, ठीक है, आपने यहाँ से शुरू किया, ठीक है, क्योंकि आपकी हाइट यहीं तक है, आपने यहाँ से शुरू किया, आपने ऊपर छोड़ दिया। जब वो ऊपर साफ करोगे तो देखो ये क्या होगा, नीचे पे आ जाएगा, नीचे पता जाएगा कैसे पूरा, ठीक है। तो आप ही चाहिए होगी, ठीक है, ठीक बताए समय में। तो एक जगह से ये मार्क्स हटाने बहुत ज़रूरी है, इसको हटाने पड़ेंगे। और ये अभी मतलब इसको तराशा जाएगा, जब साफ़ किया जाएगा ना तब आपको समझ में आएगा कितना क्लीन ये लगेगा करके। अभी बहुत है, और ये रूट्स को काटना है, ठीक है, खींचना नहीं है, ठीक है। इसको खींचोगे तो पूरा मैट्रिक्स साथ में आएगा, पतला पतला रूट है, कैंची से ही करना पड़ेगा आपको। जैसे ही मैं बहुत हल्का हाथ चला रहा हूँ, ठीक है, बहुत लूज है मटीरियल, साफ हो रहा है। ये कॉन्टैक्ट एक ही नज़र आएंगे आपको, इसके ये कॉन्टैक्ट और ये कॉन्टैक्ट अलग है, ठीक है। तो कॉन्टैक्ट्स पहले एस्टैब्लिश करेंगे, आफ्टर दैट वी विल गो फॉर मैपिंग। तो मैं ग्रिड में प्लॉट करूँगा फिर उसको, हर ग्रिड का एक ग्रिड बन गए यहाँ से ना, ठीक है। तो वो मुझे देंगे यहाँ से ग्रिड में इतना आया, इतना से इतना आया, तो वो पॉइंट मार्क करूँगा मैं, तो उससे मेरा पूरा स्केच तैयार होगा। द सेकेंड वे इज दैट फोटोग्राफी। So now we are cleaning the trench. This is what we call nijiti kamas. So with this we will scrape the trench and try to make the wall plain, clean, because we have some marks of the digging machine here, which will hinder us in identifying the layers. So that need to be cleaned very carefully and very quietly and with very gentle hand. So all this clean material which has been falling on the wall has to be cleaned properly, and that will help us in identifying the contacts, and that's what probably will be able to do in 2 days or so. Mark here, so we are removing here, you can see this with the very soft hand. Then we will try to also take some samples of charcoals. You can see here there's a charcoal here. This we will date. This will give us the age of at least we will be able to bracket the event with this. काफ़ी बड़ा हो सकता, मतलब 7.5 के तो ऊपर ही है ये करके इसको ले लें।
अच्छा, 700-750 ऊपर का ही होगा।
हाँ
अच्छा, मतलब ये थी सतह,
ये जो है ना, ये जो ग्रेवल्स हैं सारे वो इस लेवल पे थे पहले।
अच्छा,
देखिए यहाँ से, अरे वो सीजर ले आना थोड़ी सी,
ये ला थोड़ी सी बस भी करना।
ये आप देखेंगे तो यहाँ से ये ऐसे करके ऊपर जा रहा है, ये ऊपर पूरा गया है। तो ये जब क्या होता है कि आपका लेयर्स हैं ये हमेशा हॉरिजॉन्टल रहती हैं इसे।
अच्छा,
ठीक है, तो ये हम लोग ऊपर वाला हिस्सा देख रहे हैं, तो जब भी भूकंप आता है तो ये उसके ऊपर चढ़
ऊपर चले
जाता है।
जाता है बिल्कुल।
ठीक है, तो ये जो हुआ है ये आपका, हम लोग जो कहते हैं टेक्टोनिक प्लेट्स का मूवमेंट जब होता है तब ये आपका मूव करता है इस तरह से। तो
ये यहाँ से ये ऊपर चिड़ी
ये
है
पूरी ऊपर चढ़ गया। तो इसीलिए आप देखेंगे तो ये पूरा ये हिस्सा जो बना है ऐसे करके, ये पूरा हम लोग कहते हैं इसको फॉल्ट स्कार्प। ठीक है, ये फॉल्ट स्कार्प पूरा बना है इसकी वजह से तब। तो यही चीज़ें हम लोग आइडेंटिफाई करते हैं सैटेलाइट डेटा से लेके, और उसके बाद हमने जैसे ड्रोन से भी हम लोग काम करते हैं, उससे देखते हैं कि लोकेशंस कहाँ हैं, क्योंकि पूरा चलना तो रहता ही है, हम लोग चलते हैं पहले, लेकिन एक आजकल की जो टेक्निक आ गई है कि हाई रेजोल्यूशन सैटेलाइट डेटा है, तो उसको हम लोग 3D में देखते हैं करके, क्योंकि ज़मीन जो है उसका रिफ्लेक्शंस सेम दिखाई देंगे हमको अगर 2D देखेंगे तो, लेकिन 3D में ऊपर नीचे हुआ होगा तो नज़र आएगा करके। तो वो लोग हम देख के इसको यहाँ पे करके फिर GPR हमने किया यहाँ पे, ग्राउंड पेनिट्रेटिंग रडार, तो उसका भी हम लोग आपको दिखा देंगे उसको कैसे दिखता है। जब 200 का यूनिट लेके आना, लेयर्स डिपॉजिट होती हैं, ये नदी के पत्थर हैं पूरे।
अच्छा
तो ये जो जगह थी यहाँ पे पहले आपकी डबका बही थी।
अच्छा, पहले तो आपका
पहले
यहाँ
डबका
बही
ही
थी।
इससे पहले डबका जो है ये हमने पूरा स्टडी किया है इस एरिया को, पूरा कालाडूंगी एरिया जो है, तो इस फॉल्ट लाइन को हमने कालाडूंगी फॉल्ट बोला है,
अच्छा
नाम दिया है हमने कालाडूंगी फॉल्ट। ये हमने करीब 2007 या 2008 में एक पर्चा लिखा था यहाँ पे, गेबॉट होल पे हमने कुछ काम किया था, लेकिन उसमें जैसे आपसे भी बात कर रहे थे कल के कि 1505 का यहाँ भूकंप आया है कि नहीं आया है, उसका थोड़ा सा पुख्ता सबूत हम लोग चाहते हैं कि हो करके, तो वो बहुत इम्पोर्टेंट होगा। तो
अभी ये इससे देख के लग रहा है कि उसी समय आया होगा यहाँ।
अभी इसकी जब तक एजेस नहीं आ जाती हैं तब तक हम लोग कुछ नहीं कह पाएंगे, लेकिन हाँ पुरानी एजेस हैं उसके बेसिस पे हम लोग इतना कह पा रहेंगे कुछ है यहाँ पे। ठीक है ना,
इसको यहीं पे दिखा।
तो ये पूरा हिस्सा जो है इसके ऊपर चढ़ा हुआ है। अभी क्या है कि हम लोग अगर ये देख रहे हैं कि जो हमारे लेयर्स डिपॉजिट होते हैं इनिशियली वो हॉरिजॉन्टल होते हैं। ठीक है, तो हमारे पास यहाँ पे लेयर्स थे, ये मान लीजिए ग्रेवल का जो लेयर हम बता रहे हैं जो कोर्स वाला है ये वाला, ठीक है, उसके ऊपर ये सैंड बैठा हुआ है। अभी मैं इसको डिफॉर्म कर रहा हूँ, जो कि इन नेचुरल डिफॉर्मेशन जो हो रहा है करके, तो ये कैसे होगा, पहले ऐसे जाएगा ये ऐसे बनेगा,
डिफॉर्म,
ये डिफॉर्म हो गया। ठीक है, तो इसको हम लोग कहते हैं फोल्ड। फाइनली ये क्या होगा, इसको और इसको दबाएंगे तो ये प्रेशर तो बना जा रहा है आपका दोनों तरफ से, फिर ये फाइनली आपका ये ब्रेक होगा। ठीक है, हाँ वहाँ एंड हो रहा है, यहाँ से आपका ये लगेगा ऐसे। तो इसका जो देखोगे तो ये कुछ ऐसे नज़र आ रहे हैं, ऐसे ऐसे करके आ रहा है। ठीक है, तो ये कॉन्टैक्ट यहाँ लगेगा आपका, ये अलग है,
अलग है।
ठीक है, ये अलग है। इसी तरह से आपको कॉन्टैक्ट मार्क करने, तो यहाँ से ये हो सकता है, ये आपका ऐसे जाएगा, ये आपका ठीक आ गया आपका ड्राइवर। ये तो एक ये वाला फॉल्ट हो गया, ये वहाँ तक जा रहा है रेड को, इसमें वो किया होगा। ठीक है, तो ये एक तो ये हो गया आपका ये वाला, ये कॉन्टैक्ट आप मार्क करोगे इसका और इसका, और यहाँ पे कॉन्टैक्ट जो है इसका ये अलग होगा। ठीक है, और दूर से अगर देखोगे तो ये आपको नज़र आएंगे, ये ऐसे करके ऐसे हो रहे हैं। ठीक है, ओके, अब आए इधर नीचे आ जाओ, सीढ़ी हटा दो। So we are at Dabka River, which is one of the major river in this area of Kumaon Himalaya. And what we see in this side is the exit of Dabka on the Indo-Gangetic Plain. And it is in the backdrop, if you look at, you see the lesser Himalayas, then you have the sub-Himalayan ranges, and then the Dabka has eroded or incised the Shivaliks and flowing into the Indo-Gangetic Plain. Now this is the present exit of Dabka, but where we are going to take you now after this, we will show you the paleo exits of Dabka, where Dabka used to flow earlier. And this side, if you look at, then you have the terrace. We have the terrace. We have the terrace over there, which have been incised by the Dabka River. So what we see is this portion here. If you look at, okay, this one, then this is your HFT, the part of the HFT which we say the young fault line or imbricated fault of HFT, and that is your Kaladungi fault. And this we have identified the new one, which has displaced the young sediments, as well as which we can say that which has also diverted the Dabka channel from its old path, okay, where it used to flow. So what we call is basically the wind gaps, okay, or the paleo water gaps of Dabka, which we will be looking on this side, because Dabka was flowing far from almost like 3-4 kilometers from this location now, and it has shifted to the side. The shifting is a process which we consider that it was because of the lateral propagation of the fold related folding. So we'll go to the next side, where you'll be looking at the uplifted river beds and the fault scarp. So fault scarp, as I told, that this is the fault scarp which runs here. It comes like that and then it ebbs. So this is this part on my right. If you look at, then we have the just across the bridge. Bridge is on the Indo-Gangetic plain, and then on the other side, if you look at across the bridge, then you have that is the Indo-Gangetic plain side, and this side we say this is your the uplifted shivalics, or the young deposits which were been displaced by the KFT or Kaladungi fault. So what we see is the cliff. This is the river bank cliff, but the incision is because of the base level change. And so what we do is we try to take in the higher side on the backdrop, you see in the upper ridges again another higher cliff is there. So we try to date those sediments, and that will help us in fixing up the time when the sediments were deposited, and the later phase was the phase of the incision or the down cutting, and that can be related to your base level change. And the base level change, as I told earlier also, that it could be tectonic or it could be climate change. But since we are sitting very close to the Himalayan fault, that is Himalayan frontal fault, so this could definitely we say that this could be related to your tectonic activity or the upliftment what has occurred. So the portion from this side is riding over the Indo-Gangetic plain. Okay, and then whenever there is another earthquake, it will rise again and slip. Okay, so this is what the process keeps going on, and that's how we have seen the building up of the Himalayas here. So again, what I told, that this is HFT, Himalayan frontal thrust, and this marks the present plate boundary between the Indo-Gangetic plain, or we can say Indian plate, and your Eurasian plate. So this is the active plate boundary. So now we are again in the bed of Dabka, in the river bed of Dabka, and what we are doing is we are trying to take the samples from the incised cliff or the bank of Dabka, and trying to come up with an age which will help us in understanding that when exactly the incision started. Okay, and that can be correlated to the tectonic event or the uplift event in this area. So if you see, I will show you now the cliff there where the students are climbing up, and that what we see is the incised phase of the river bank, and we will take the two samples, at least two samples from there, which will try to help us in bracketing the age of this terrace particularly, which got incised by the Dabka channel. So they will take two samples, one from the gravel layer, which is the shape of the based on the contact and the shape. If we see, this is what is a typical channel fill deposit, and the channel has flown at some point of time at that height, and then what we see is the incised cliff. So that will help us in identifying the age of the sediments. So now we are basically taking the samples, the sediment samples, which we will date through OSL dating technique, and that is optical illumination, optical stimulation illuminations technique, and that will give us the age of the sediments when they were deposited. So basically we are going to date the quartz, which usually when get buried with the sediments will give the age of the depositional age, because after burial then it will keep on acquiring the energy from the radioactive material in the sediments. So this sample which we will take should not be exposed to the sunlight, hence we are collecting the samples in the pipe. So if you can zoom in, then you will be able to see that they are using the metal pipe, which doesn't allow the sediments to get exposed. And this will be put the one pipe which they are hammering into the wall is at the base, or we can say just in at the contact of the gravel and the soil unit. So light brown soil, on the top of that we see slightly darker color material, and at the base is your gravel deposit. So you have that portion we will date. That will help us at least in understanding that when the sediments were deposited. So if we get the age of this, after this we can talk about that the abundance of this the channel flow, and then the phase of incision followed by that actually. So that will help us in understanding and bracketing the event exactly when it took place. And this area is basically, we will go to other location as I told in the beginning, which is much more fascinating in the sense of having more clear example or clear evidence of the faulting. But this is just we are hardly how much, maybe 150 meters towards north from the plate boundary, and we are very close to that. So now we are almost done with the trenching part, and this what we have excavated the trench, almost like 26 to 27 meter long trench, and if you see the depth is ranging around 3 meters to 2.5 to 3 meters we have, and this is the portion where we got the deformation. Now after the trench was dug, we cleaned the trench using Nijiri Gamma. We use this tool, Nijiri Gamma, for leveling the wall surface, and then also use the brush. We can also use water to spray on or sprinkle on the wall, but sometimes it is not good because you have a very loose matrix in the gravel layers, and that can go down. So we can use water, but in this trench we have minimized using water, and mostly we have used brush to clean the walls, and that is important to identify the different layers. Okay. So the deformation, as I told, is there. So the gravel which you see on the top has righted over the soil which you see here. Okay, the soil. So the soil is capping the gravel, but now the gravel is capping the soil. Okay. So the gravel has moved up along a very low angle fault. That's what we call the thrust faults, very low angle thrust fault. And we see two strands. One is on the top here, and then another one is the base where the gravel is been riding on the soil. So now after the cleaning, what we did was we grid, and this grid which you see is in 1 by 1 meter grid, and this will help us in measuring exactly the amount of displacement and the thickness of the layers, and wherever we see the cross-cutting relationship of the different layers as well as the contact of different layers in this particular grid. And this grid we will put on we'll be using to sketch the trench, and preparing the sketch we will use a tracing sheet. Again we will put 1 by 1 meter, and on a very small scale we will sketch the trench. The other part which is remaining is before we get into the collecting the samples and all that, we will take the photographs very closely, very high resolution photographs, and we will mosaic it in the lab. So mosaicing is again another very important aspect of this study, because that will help us again in preparing the final sketch. We can use the sketch which we have prepared in the field by marking the contacts and with the help of the grids which we have done, but also you can do when we are having very high resolution photographs. That can help us in marking the contacts. Now this is not the right time to do the photography, because the sunlight is on the wall, so we need a very even sunlight here. So what we will do, we'll wait wait until the sun goes down, and in the evening, or maybe in the around 4:30 or so, we will try to photograph this trench, very close photographs, as well as we'll take overlap of the photographs here. And then after that we'll go for sampling. So once the event horizons are identified, for example, there are more than one earthquake here, but the most recent earthquake you see is the humus-rich soil is also been deformed. So that is the event horizon of the most recent event, which occurred maybe 400 or 500 years back or so, but we have not dated until now. So that we'll try to collect the samples from here. We'll collect the sediment samples for OSL dating, that is your optical stimulation illuminations, and also we will try to collect wherever we'll find the charcoal. So charcoal will help us in bracketing the events, and the OSL ages of the sediments will give us the age of deposition of when the sediments were deposited. So we'll try to take the sediments samples and the charcoal samples from the hanging wall. So this side is the hanging wall where I'm showing my hand. This side is the upside is the hanging wall, and this is our footwall here. So we are standing on the footwall. So we'll try to take samples, as many as we can, from the hanging wall as well as from the footwall, and we will also try to measure the angle of the fault. What is the depth of the fault with respect to horizontal, and then we will also measure the shear fabric wherever we see a prominent in the gravel, and also we'll take the amount of displacement along the fault. So at present, if you look at the total displacement, which we can roughly try to tell you, is almost like from the base of the gravel, and the gravel which is overriding and even cutting the humus-rich brownish black soil, that much is almost like the displacement is 1, 2, 3, 4, and 4.5 meter or so. And the throw of the vertical throw, which we see from the base, because we found the gravel here at the base, so we have the gravel. So if you take the top of this gravel and then top of the scarp there, because that is also comprised of the gravel, and those two gravels are the same, so that throw will be more than 5 to 6 meters or so. So 5 to 6 meters possibilities are there that that can happen in one single earthquake, but we believe that may not be in a single event. So we need multiple events to create such a high scarp. So if you see this the profile of the scarp from the top here, so you have the slope, then there is a break in the slope, and then there is another slope, and then there is a break. So this itself indicates that these two scarps were formed in two different events. So having multiple scarps like this is very important, but most of the time we may not get the scarp because this will get eroded very fast. But luckily we got two scarps here, so at least we can say that minimum two earthquakes in this area or on this fault have occurred in the past, which has given rise to the formation of the two scarps here. So this is what we will be able to tell after doing the dating, as well as we'll do the slip measurements which we have collected from the trench itself, and based on that we will do some geometric calculations which will help us in understanding that what is the slip during single event, and what will be the vertical throw during single event. So we'll use a simple trigonometries, and then we'll based on the average angle, because that is important again to have the understanding of the deformation pattern. Because if you're having low angle fault, then what we see here, then the slip will be less but more will be consumed by the folding. Okay, and that's what we see here, because most of the slip has been consumed by folding and less has been transferred on the fall plane. So that part also we will have to take into consideration, and that we will be back calculating based on the height of the scarp from the base, that how much is the vertical throw. That will help us in back calculating the slip per event also. So these are things which we will be doing, and we'll try to show you at the final one when we are collecting the samples, how we have collected the samples. And the samples collection will depend upon that how many units we have identified, because that separation of different unit or the contacts, based on the contact the different units are marked, we need to date those layers. That is important to reconstruct the paleo earthquake history. Now final here, one thing which I will tell you, that suppose not we can find out from here itself. So as I told that the last event deformed the brownish or dark soil, humus-rich soil, and then top you see is the lighter one, which is the capping unit. So at least based on if we date the soil here and the capping unit, we'll be able to bracket the event, that when exactly the event occurred. So if you are having, for example, the charcoal age or even the OSL age, then we will try to take the minimum age of the soil, because that was the last when the soil finally got deposited and buried under the overlying unit or capping unit. So we'll take the minimum age of that and the maximum age of that one again, because that we need to have the older age of that unit at time it started depositing. Because as you move up vertically, then you will see the younging sequence. Okay, so you have the older sediments, then younger sediments, then youngest one. So we'll try to take the minimum age of this and maximum age of the capping unit. That will allow us to bracket the event. So that based on those calculations like slip and the vertical throw and the horizontal shortening, we'll be able to talk about the magnitude also, because there is an empirical relationship which talks about or gives us an idea that what amount of slip will be required by a particular magnitude earthquake. So that will also help us in talking about the magnitude of the earthquake. And as I told that we will be getting the minimum slip here, because most of the slip has been getting consumed during folding at the time of the movement. So that we will do by the vertical throw and the development of the scarp. So this we will be able to reconstruct the complete history. So you can see now, right now, what we are doing is that we are so this we consider as an uh, west facing wall or east wall, you can say, of the trench, and this side we are having the east facing wall or west wall. And right now we are putting grid on this wall also. My students are working hard to do that. So we'll prepare grid again. We'll photograph when the sunlight is low. So we need to have a very even light on the walls that will help us in getting the contrast between the different units. Okay, gravel and sand we'll be able to differentiate, or sandy soil we'll be able to differentiate well, but there are few like contrast which we need to look at in terms of the color as well as the grain size of the material. We'll try to differentiate different layers. So that's all from now, and we'll get back to you when we are collecting the samples, and we'll show you how we have collected the samples for the OSL dating and how we do the packing. And another part is that how we collect the charcoal sample and how we do the packing. Okay.